Today we have with us Jeffrey Goldberg from 1Password. I'm going to say you're becoming a permanent resident of PasswordsCon, more or less. And Jeff always have interesting talks, in my opinion. He's a great guy to talk to as well. I know he loves getting questions, so prepare every questions that you have for him after the talk, or also initially in the breaks afterwards as well. He's here to talk about, can a password management service safely learn about users' passwords? Take it away, Jeff.
Hello. Okay, you can all hear me? So first of all, it's really great to be here. It's great to see Per here. It's been a while since you've been in Las Vegas at these conferences. And as he said, I've actually, been part of PasswordsCon one way or another for a long time. And I remember my first talk was in 2013 over at the Golden Nugget. And I was the first talk on the program other than Per's introduction. And, I'm a dilettante academic. That's really what I am. I'm a PhD dropout in linguistics from a long time ago. And things went to sleep. Okay, I hope the things that went to sleep are not you, or at least not yet. Do I need to plug this into power for this? There we go. Okay, so I'll just do stuff. Okay, so I'll fiddle here. So it doesn't, that's not what I wanted. Okay, I won't do that. So I came in, I had no idea what the audience was going to be like, or I had an idea and I was wrong. So the first talk I ever gave at a PasswordsCon was basically math from beginning to end. And so this time, I'm talking about something that could involve a lot of math, and I've left all of it out. So, anyway, so that's it. Now, one of the things that Per just said, he said that people are often reluctant to give honest answers to certain sorts of questions on a survey. This is, in some fields, called the social desirability effect on, in survey design and what we do. And as it happens, I'm going to be talking a lot about soliciting honest answers to very sensitive questions. Okay, so let me just set the scene. I am Jeffrey Goldberg. I've been working at 1Password for 12 years. I can do subtraction. I really want to know everything, and there are certain things that I absolutely do not want to know. And we'll get to that. Now, 1Password is a password manager. We have client software that people run on their own devices, and a service used largely for synchronization, but for other things as well. The client software is where most of the action is. This is all just background. I should have a kitten up there. I don't. But just imagine a kitten if you know all of this stuff. The unlock client knows certain things like the names of your vaults and the titles of your items and those sorts of things. The server doesn't. And the unlock client knows the strengths of your various passwords to the extent that password strength can be measured. We've talked about that elsewhere and at other conferences. Client, so all of the usual stuff. And the overall design and architecture of the system is so that we know as little about user secrets as possible. But we also think that we know a thing or two about password behavior. Maybe by relying on shitty surveys. Or maybe not, but we certainly have opinions, and we certainly believe that we know something about password behavior. Broadly, one of the things I'm interested in is what can we learn about a 1Password user's behavior without putting them at any risk? And what technologies for doing so are within our reach? And so I'm going to actually present a sample research question because it gives an extreme case. If we can understand and research this and look at this, then we can pretty much do anything safely. So something that I've said at previous PasswordsCons is that people who enable 2FA for their password manager will tend to use weaker account passwords than they otherwise would. And I've given a couple presentations about that and why I believe that, and other things about misunderstandings of what multi-factor authentication does and how those get implied, and how that impacts the case of using it for a password manager. Doesn't matter whether you believe me or not, doesn't matter whether I believe me or not. I would like to know whether that's true. So in more research terms, is there a negative correlation between use of 2FA for 1Password itself and the strength of the account password? Now, I'm going to tell you, I'm not answering this question today. We don't know. What I am actually going into, well, fine, that's a few slides later. We do know whether a user has 2FA for 1Password enabled, because that is something that is done server-side. We do not know the password strength of anybody's account password. And we really don't ever want to know the password strength of anybody's account password. We don't want to put anybody or anything in a higher risk of cracking against their password. So I don't really think I need to list the reasons, and that's also largely because I was putting the slides together on an airplane and I decided to skip this one. Okay. So, so there are things that we don't want to know, but we also want to make it absolutely clear that we don't know and that we don't have the capacity to know. So not knowing is not enough. People need to know that we're ignorant of these things. Okay, so I've been thinking about this problem and this example, and what you're going to get is a more or less what's a preliminary progress report on my thinking with no actual answers to the questions. And for those of you who are familiar with differential privacy and embedded in those communities, everything I say here is going to be, most of what I say here is going to be a review of what you already know. And so I won't be insulted if you get up and walk away. But hopefully, even for you, there might be something new or interesting here. Or at least you can correct me when I'm wrong about stuff. Okay, so we have clients that have sensitive data. when they're unlocked, this sensitive data isn't decrypted within the clients only. And we want to do some data analysis, across a broad number of users. And so the general structure is that the client would do something with the sensitive data and then report it up to some service outside of the users and client's control. That's the structure of how gathering such data would work. And, everybody's first correct reaction is, well, you collect the data, but you keep it anonymous. You remove all identifiers. You can remove all identifiers that the client sends. You still have IP addresses unless you go to other measures to not have IP addresses. So potentially something like this could be done through Tor or something similar. Again, saying is that, yes, we could promise to remove IP addresses, but we want this to be transparent to the user and the security community that these privacy guarantees are there. De-anonymization is a real thing. So anonymization is hard in the first place. The common practice of simply hashing the identifying information is bad, breakable, reversible for reasons I'm not going to go into here. It's really common. It's just not the way to do such things, but there are ways to do it. You should design your system under the assumption that your data will leak. Again, this has been a principle that we've used at 1Password since the beginning. But anonymized data, even properly anonymized data, when combined with other data, can be de-anonymized in very important and surprising ways. And depending on time, I'll run through an example of that at the end. Very famous case with Netflix, but it really is the case. And that other public data that things get combined with is data that comes from other places, not from you. You have zero control of it. You've got zero control of the publication of that other data. And furthermore, you have to design your system to resist de-anonymization when the anonymization could be against public data that doesn't even exist yet. So de-anonymization is a thing, which leads to this major point, is that good anonymization and data protection is absolutely necessary, but they are far from sufficient. So one approach is to simply have the client answer vaguely. Instead of giving you the precise password strength to the extent that the password knows it, it could lump it into, let's say, one of three bins, a low, medium, high. So you add some vagueness to it. But additionally, there's the notion of what is called the random response technique, which is actually, in a sense, a precursor to differential privacy. And it goes back to the 1960s. So this example I cite here is from a paper in the 70s. So subjects were given a questionnaire, but told to roll a die before answering each question. And if they rolled 1 through 4, they were supposed to answer honestly. If they were to roll a 5, they were supposed to answer yes. And if they rolled a 6, they were supposed to answer no. And this increased response rates, and through other analyses by comparing with other methods and statistical cleverness, you could see that it actually increased honest response rates. So again, in a sense, the randomness of this was transparent to the user and made them feel safe answering honestly. Another study conducted in Mexico in 2001, where abortion was highly stigmatized and illegal, used another form of random response, and people were given a red and green question, and they pulled a red or green thing out of a sack. They knew that there was just one red and green thing in the sack, and if they drew red, and of course the researcher, the interviewer, did not see what people drew, and this was again transparent to the subject. They answered, did you ever interrupt a pregnancy? Or green, were you born in April? Now, from census data, they knew how many people women in this age group were born in April, and were able to do some statistics on this. And I've got it in my speaker notes, which are not displaying here, but I think it was around 16% of women in this range in a sense. Anyway, so they estimated for the population, given the way they sampled, that 16% of women had an abortion. Okay, and so various statistical techniques here. Various statistical techniques here have demonstrated that this stuff is effective at getting more honest responses, and it does that enough to easily make up for the statistical noise introduced by this. And in these cases, went the wrong way. So let's suppose we were to set up a system that answered honestly about password strength 50% of the time, and otherwise pick, let's say, the 3 bins randomly. If our data leaks and is de-anonymized, is the user sufficiently protected? And the answer is, I don't know yet. But that's for later, because I haven't looked through the order of my slides. Okay, so these techniques add statistical noise. They reduce the statistical power of the tests, and the consequence of this is that you either need a larger sample, or you end up with wider confidence intervals. Okay. Now, where differential privacy comes in, differential privacy, it's really, really hard to explain what it is without the math. So I'm going to try to explain what it attempts to do. And it is about limiting the possibility of de-anonymization. It's an anti-de-anonymization technique. And it provides a common mathematical notion of the protections of some data set in this respect, but across a wide variety of techniques and uses. It does add statistical noise in ways that are similar to the vague and random response stuff. And the noise it adds is designed to have certain statistical properties that make it easy to combine, easy to reason about when you combine it with other things. Okay, it is not a single technique. It is not something that is only done at this stage of some data analysis and collection. And it is not particularly easy. So when I said that it can be applied at different places, or implied that it could be applied at different places, it can be done at data collection time. It can be done to transform a data set that you have that does not have privacy guarantees into a data set that does have differential privacy guarantees. And it can be done at query time. You've got a data with sensitive data that is at risk of de-anonymization, but it's also differential privacy can be applied as what analyses you do on the data and adding its magic noise to those queries so that the reports you get out of it could be safely published. Now, there are really, really nice tools that are coming to be available and usable by people who don't have PhDs in math. For the third one of those, and to a lesser extent, the second one. But in our case, we never want to have the data in the first place. So we need these things to be applied and done by the client. And what would be required if we're to go beyond the random response stuff would be something called homomorphic encryption. It's a fancy, scary name for actually magic. I'm sorry, it's just magic. So the paper that first introduced it without this terminology was in 1982. And it set up the question, 2 millionaires wish to know who is richer. However, they do not want to find out inadvertently, and they do not want to find out inadvertently any additional information about each other's wealth. And I should also add that they do not want any third party to know either. How can they carry out such a conversation? So when you look at a problem like this, you would say they use a trusted third party. The trusted third party will learn the wealth of each. Also, millionaires seem to have been different back then. Now they would be boasting about them. Anyway, never mind. I need to stay on track here. Okay, so, so the normal way of thinking about this is that you have a trusted third party. You do various things to ensure your trustability of that third party, but the third party gets both numbers and then simply reports back who's richer. And I keep on doing that. Okay. Well, the particular paper there developed a technique to solve this problem and a bunch of similar problems without the need of a trusted third party. And yeah, no math, magic. It's done by magic. But it's done by magic in polynomial time and space. And that is very important. And in general, it was proven in subsequent work for this paper, for any protocol that can run in polynomial time using a trusted third party, there's a protocol that can produce the same result without the trusted third party in polynomial time. And so it allows multiple parties to compute things over their individual secrets without revealing those individual secrets to each other or to a third party. And so this is generally what homomorphic encryption is about, multi-party computation. So the practicalities of this stuff. I still think it needs a PhD to make real use of it. The libraries and tools are getting better, but yeah. Polynomial time and space doesn't actually mean fast and small. And so even though the theory of this stuff was developed 40 years ago, the reason that we're only seeing these techniques used in the last 5, maybe 10 years is because it actually takes a lot of computation. And the protocols used actually have a lot of back and forth. They're complicated protocols. So I'm going to say that that technique is still beyond our reach. When I started investigating, I was hoping otherwise, but we're still there. Now, I do want to make an aside on the adding noise. So sorry, I know you're all passwords people, and here I am talking about stuff. But again, focusing on the example of anyone who's doing research into users' behavior of passwords, all this stuff is relevant, even if general to many other cases. One of the objections so there have been cases where people have provided differential privacy techniques as a real, clear, viable, usable alternative to what systems are doing, and their clients, the people that they were developing this for or trying to get to use it, I got ahead of myself, would complain about the statistical noise added. These techniques add noise, but they add a quantifiable and well understood amount of noise. And so you either need a larger sample or you accept wider confidence intervals. But I've heard cases, usually from other people who've been trying to get this to work, where they run up against people saying, we can't accept anything with statistical error or confidence intervals. Well, if you're doing data analysis with or without this stuff, you have statistical noise, error terms, confidence intervals. That is simply a part of working with data and doing any analysis of it. And so my big mean rant is this: if you can't handle statistical error, or you don't know that you always have some, you should not call yourself a data analyst. and I am being far less polite than the people I know who've encountered these objections. They couldn't say it, I can. Partially because nobody's hitting me with the, oh, we can't do statistical noise stuff. If people were hitting me with that, I probably couldn't get away with saying this. Okay, and that's also an indication of why I don't have friends. So, conclusions. Is there a combination of, there should be an of in there, a combination of vagueness, random response, and data protections on the acquired data that would offer sufficient guarantees for our users and allow us to answer the 2FA strength question with sufficient confidence? I still don't know. This is a work in progress. I thought that I would be able to figure out how strong of an effect there'd need to be in the real world about those things, combined with these techniques, to then estimate what sample sizes were needed. But my math isn't quite up to the task that I thought it was when I started the project. Okay, so I actually finished, Netflix case, right, okay. So I actually finished the guts of my talk much, much earlier because I only noticed a couple days ago that I had 55 minutes instead of 25. But I think it's useful to go over the Netflix case of de-anonymization that I talked about. Again, I'm sorry, it's not really passwords, but it's about preserving user secrets. So way back when, good, I have it on the slide. In 2006, Netflix really wanted an algorithm, or to improve their algorithms at predicting what things to recommend to people. And so they publicly released an anonymized data set of about 100 million movie ratings from nearly 500,000 subscribers. And all customer identifying information has been removed. All that remains are ratings and dates. Now, people might have dozens or maybe 100 different Netflix ratings at the time, or maybe more. But people also rated things publicly on IMDb. Now, they will have, for the IMDb stuff, they knew that that was public, and so they were okay letting the world know that they watched that. If they also watched, if they watched again and again and rated highly Nickelback's world tour, that's something that, you wouldn't want anybody to know about. And there are other things that people might watch that, that they don't want the world to know that they watched. But they rated them with Netflix, but not with IMDb. So a paper in 2008 showed that even with just a tiny number of IMDb ratings, you could de-anonymize almost all of you could de-anonymize almost all of the Netflix data. And so this is why I wanted to emphasize that de-anonymization is a real thing, and it is against data that may not even exist yet when you are designing your system. And so differential privacy is designed, in a sense, to add a certain amount of noise to, let's say, the data that Netflix published in ways that would prevent this or any other kind of de-anonymization. Okay, and there are other examples. There have been many, many more cases of de-anonymization, but that one is really dramatic and much simpler to explain. So I don't have an answer for those running password managers who want to study their users' passwords behaviors. But it's not fully out of reach. It's just not quite within reach yet. But these are the kinds of things you need to look out for when designing such a system. And with that, I will take questions.
Thanks, Jeff. I'll ignore the homomorphic thing because I don't have the math either. But when you talk about adding noise to a measurement in order to add a little bit of uncertainty about the answer to the question, in the case of maybe the master password for your password manager, the reason that you might be sensitive about the answer really has to do with whether, am I an easy target to hack or not? If you're adding noise to it, aren't you? If it's additive noise, don't you still end up with just a larger probability that you're easy to hack?
The noise can have a negative sign, if that answers your question. No, okay, in that case, I've misunderstood the question. So the noise can add or subtract values, but obviously I've misunderstood the question.
Right. Well, let's say that you have a scale of 0 to 10 for the strength of your master password, where 0 is you used pairs license plate, and 10 is you used something that was really, really good and long, probably. If you're adding a certain amount of noise to it, and you end up with an answer that is 8.5, it's still likely that 8.5 came from the fact that the original number was 10. On the other hand, if you end up with maybe it depends on the distribution of the noise.
Right. So two things. One, yeah, okay. So yes, you can, if the data is de-anonymized, then you can make broad guesses of the true value based on the reported value. So you combine this, and in a sense, you have to be able to do that for there to be any data analysis possibility whatsoever. So that's why my question of whether something like the random response thing is with the data protections, with the anonymization, is enough. And it's why my answer to that question is I don't know. You use wide bins, so you wouldn't ever have a report like 8.5 on a scale of 10. I was thinking much more of a 1, 2, or 3, and the integer values. So you have a vague response, then additionally the noise, but yes, the question is are you still leaking if this data leaks too much information. And I don't know, and I don't, it's hard to quantify the notion of leaking too much. There are ways to do it in differential privacy terms where you can at least know how much you're leaking. And so we can analyze this to know how much we're leaking. But in the end, it's a whole big risk analysis thing. So maybe, with what you say is what I'm trying to do here is impossible. I hope not, but I recognize the possibility that what I'm attempting to do here is impossible.
Yeah, so I have a question myself. I was just wondering, thank you for the presentation, by the way. It was great. I'm curious, from your comments regarding it's being impossible but close reach, are you currently researching this? And if so, where are you with your current research?
So when you say researching this,
The topic that you're referring to regarding data leakage and whether or not to analyze users' passwords.
So this is a work in progress research report where progress is just beginning. But I'm trying to at least put up stuff. And right now it's just like placeholder documents. But this is this repo here. Again, it's mostly placeholder documents and the slides for this talk once I merge them into main. On privacy preserving analytics. So yes, we're researching it, but it's slow, it's preliminary, it's just at the beginnings.
Jeff, great topic, very intriguing, so thank you very much. Let's say to answer that question, we compute the entropy on client side for the password, and then we encrypt the entropy answer, whether it is high or low. Let's say we don't have 3 values, but just 2, high or low. Using homomorphic encryption, especially the one that is used for e-voting, is called pi-layer homomorphic encryption. Pi-layer homomorphic encryption, and then send it to the server side. On server side, we don't have to decrypt the ciphertext to know the value, whether it is high or low. Just by applying the same e-voting verification scheme, we can find out whether the password has low entropy or high entropy, and then correlate with the 2FA.
Okay, so I was not aware of that technique. But if I understand correctly, there are tools and known techniques for collecting binary data. And so if we just take this as a high or low binary, then there are tools you can actually use. Thank you very much. You have my contact information. Please send me the actual link.
Any more questions for Jeff? No. Okay, so thank you once again, Jeff.